I said at the end last time that we were going to talk about a new type of machine this time. Let's get to it. So this is a machine for context-free grammars. You know, we've had machines, like we started off talking about DFA, NFA, and now we know those are machines for regular languages. I shouldn't say CFG, I should say CFL. NFA, DFA can only ever make regular languages, and so they are fairly limited from that point of view. We have been talking for the past week or so about context-free languages, which are much more general, like there are more things which you can express using context-free languages. What I want to talk about, at least briefly, is a machine that can give you those languages. So there is a type of machine. It doesn't actually look like NFAs or DFAs, so it doesn't have finitely many states. That's the major difference between NFAs and DFAs, because these context-free languages, you know, I will just say, like, for example, A to the n, B to the n. There is no NFA for A to the n, B to the n, because it's not a regular language. But there is a machine of the type that we're about to talk about. They're called stack machines. Stack machines. And a stack machine there is a stack machine associated to each context-free language. That's sort of the big deal about stack machines. Let me tell you about stack machines then. They're actually quite different in the way that they look from NFAs, DFAs. In particular, it doesn't have a diagram with states on it at all. Because if it were going to have states, it would have to have infinitely many of them, and there's not a reasonable way to draw that as a diagram in the same way. But anyway, a stack machine, the way that a stack machine works is it reads the string. I'll say it reads the input one letter at a time, as usual. I will say left to right, one letter at a time, just like an NFA or a DFA. But instead of, like I said, instead of having like a diagram with states and arrows on it, and it doesn't like move from one state to the next, but instead, each time it modifies the stack. So the stack machine, as it's reading the string, it has this like, you could think of it as a piece of memory or a data structure called the stack. And if you've taken like a computer science data structures class, this is the same as what they mean when I say a stack. So you may be familiar with this. But if not, that's totally fine. It's not a complicated idea. So it modifies the stack. The stack is a bit of memory, but it's very limited. So it's the stack machine memory. The stack machine is not able to just remember anything. Like, this is not a general purpose data structure like your computer has a hard drive or something. But the stack machine is a type of memory which works very specifically, and we're not usually going to draw pictures like this, but this is sort of a picture diagram of a stack. You're supposed to imagine the stack is like a pile of things sitting on the paper or something. And this is a stack, and the restriction about how the machine uses the stack is that a stack, just like a pile of papers, you can only see the top thing. You're not allowed to like reach down into the middle and look in the middle of the stack. You're only allowed to modify on the top. So the stack is a type of memory. You can only modify the top of it. The top of the stack. All right? That's why it's called a stack. You should imagine a pile of papers. Or you could imagine like, I saw a stupid video of a guy putting on like 100 t-shirts at once. It's kind of like that, where if you want to, modify the t-shirts, you got to just take the outer one off first, and that's the only way that you can interact with the structure. All right. So this is what the stack looks like, and allowable operations. there's actually just 2 allowable operations, and they have cute little names. So one allowable operation would be to remove the thing on the top, and this is referred to as pop. This, I would say, what exactly happened in that step? I would say you pop the D. The D is the thing on top of that stack. I'm thinking of the top is the top, all right? And then, anybody know about stacks? You can also put something onto the top that wasn't there before. Anyone know the word for this?
Load.
It's not load. Maybe I've never.
Queue. That's what we use.
Oh yeah, it's push. This is what I've always heard. The other operation you're allowed to do is what we're going to call push. This, I think, is pretty standard in programming. You use stacks in programming, not if you're like writing, here I said push X. If you're writing using a fairly like modern programming language like Python or, I don't know, Java or whatever, you don't typically use stacks by hand, but stacks were very common in the old days, or if you want to write code in very low-level programming languages, stacks are super important in the way that they work. A typical compiler or interpreter will use a stack to keep track of where the code is, where the execution is jumping from one place to another in the code. It's called the call stack. When you're one spot, but then you call a function and it jumps over to another spot and then it runs back to where you started. Those things are stored in a stack. Anyway, this is how the stack works. There are 2 operations that are allowable. They are called pop and push. So pop is the one where you remove something from the stack. Push is the one where you put something new onto the stack. And these operations must always occur on the top of the stack. All right. And there are other kinds. I don't know, if you take a computer science data structures class, you will learn about other kinds of variations on this. There's another one where you can only put stuff onto the top and take stuff off of the bottom. That's called a queue, because it's like a queue, like imagine people standing in line for something. People join the end of the line, but they come out the front of the line. So that's like a stack, only kind of the other way around, halfway different from a stack. And a queue has different capabilities than a stack does, and there are reasons why you would want to use one versus the other. Anyway, we are going to talk about stack machines. Now, I am never again going to write the stack as if it was like a pile of stuff like that. We're going to write the contents of the stack just as a string, and the stack will always be written sort of top to bottom. So if I were to represent these steps the way that we are more typically going to write it, I would write it this way. So the top, when we write the stack like a string like that, the top is the left side of the string, right? Just so that we don't have to constantly be writing these vertical towers of things. All right, let's just try an example of a stack machine. I'll show you how it works by means of this example. Like I said, there's no diagram. All it is a description of the allowable pops and pushes. And I said before that the idea is the machine reads the string one letter at a time, and then based on what it's reading, it modifies the stack in each step. And so the stack machine consists of, I'm going to write just sort of like a list here, or a table of things. And my first one, I'll give them numbers here. This is like rule number 1 says A, S, SX. So what that means is, if I read A from the input string, the appropriate thing to do when I see an A is to pop S off of the stack and then push SX onto the top of the stack. All right. I'll tell you, this particular machine is going to have 3 rules. The second rule is what to do if you read a B. It is pop X, push epsilon. Epsilon, as usual, means the empty string, so this means you don't push anything new onto the stack. And then my third rule is going to say read epsilon, pop S, push epsilon. that third rule is kind of like an epsilon transition in an NFA in that this is a rule that you're allowed to do even without reading anything from the string. All right? And the idea, I'll give you some little commentary over here. The stack always begins with S. All right? This is referred to as the starting stack symbol. So the stack, when you start, it doesn't have any stuff on it except just S. All right? And then you read the string one letter at a time, and each time you follow the rules. Like, for instance, if it starts with an A, I'm going to read the first A and then take away the S that I started with and put on S followed by X. All right? So the stack always begins with S, and then we do rules as we read the letters. All right, and then like, what's the goal? I mean, so the machine is supposed to take a string and either accept or reject, right? So the goal is, I will say the input string is accepted when we end up with an empty stack. That's what makes a string be accepted, all right? If you end up with an empty stack, then it's accepted. If you read through the whole string, but you end up with like stuff left over on the stack, then it's rejected. That's how a stack machine works, all right? And we're going to do all the usual things, like I show you a stack machine, and you tell me what's the language that is accepted by this stack machine, and so on. And the other way around, I describe a language to you. You make me a stack machine that has this or that language. All right? So let's just try and look carefully at this example and figure out what the language is. Let's try, on this particular stack machine, let's try AABB on this particular stack machine. So unfortunately, I may have to scroll away the rules, but I hope I'm going to try and write this down in steps here. So maybe I'll write down the input string, and then what the stack says. And of course, we begin with AABB, and the stack says S. This is sort of the initial starting configuration of the machine. All right? And then what happens after we read the first letter? So in the first step, this first A gets read. I'm going to write that maybe like, oops, AABB. Okay, I'm just going to sort of put a little, cross out the first A to indicate, like, in this step, I'm reading the first A. And then what does the stack say? Well, rule 1 from our chart up there says if you read an A, you pop the S, and then you push SX. And so the stack will now say SX. All right? The S, which used to be the only thing on the stack, you throw that S away, and then you put SX onto the stack. All right? Okay? That was rule number 1, if you want to keep track of the steps that we're doing each time. All right? Next, what happens when I read the next A? You're going to do rule number 1 again, because I still see an S on top of the stack. And the effect of that will be, okay, now it's going to be, I read the second A. Again, you throw this S away and replace it with SX on the top of the stack. The stack now says SXX. This is, again, rule number 1 that I just did. All right. Okay, what next? The next character to read is a B. Now, if we look at our chart of allowable steps here, there is a read B pop X. Actually, we are not allowed to do step 2 at this point because of the stack at this point doesn't have X on top, right? It has S on top. So you cannot do rule number 2 at this point. Actually, you can do rule number 3. And in fact, I don't know if you wanted to, but we could have done rule number 3 at any time in any of the earlier steps. This is an epsilon read. And so in the next step, I'm going to do number 3. This consists of not reading anything from the input. So the input still says just BB remain in the input. Because I'm doing an epsilon read this time, we do not consume one of the input letters. It says pop S, push epsilon, which just means don't put anything on the stack. So the stack now says XX. Right? And now we can proceed by doing rule number 2. And actually, I'm going to do it twice. So we do rule number 2 to read the next B. It'll say, I'm going to read that first B there and pop the X, push epsilon. So the stack now just says X. That was rule number 2. And then I'm going to do that one more time. Rule number 2 again. And I'll be done. The stack will now be empty because rule number 2 again says pop X, push epsilon. That was number 2 again. And since the stack is empty, that means that the string is accepted. All right, so this stack machine, it does accept AABB. Any questions about that? Yeah?
If you had B and S without the epsilon, transition would be, what would you do there? Because B pops X.
Yeah.
Encounter something else.
Right. Yeah. So I was about to say there are actually choices that I made as I was doing this. Like for instance, I could have done the epsilon read even at the very beginning, and then I would sort of immediately exhaust the stack, even though I hadn't read through the whole string. So I will be, what I said before was the input string is accepted when we end with an empty stack. I'm going to be a little bit more specific here. If any sequence of moves will read the whole string, read the whole input, and end with epsilon on the stack, then it's accepted. If any sequence of moves gets you to an empty stack after reading the entire input, then the string is accepted. And if this is not possible, and that could mean either you get to the end but the stack is not empty, or you get yourself into a situation when you just can't do any of the moves. And I think that's what he was describing before. So if any sequence of moves will read the whole input, then it's accepted. Otherwise, that is to say that all moves either leave a non-empty stack or get stuck before reading the whole string, it's rejected. All right. So on a stack machine, it actually can be a little difficult sometimes to verify that a certain string is rejected. It's not so hard to show that it's accepted. You just show this sequence of steps, which gets you to the empty stack. To show that it's rejected, though, you have to somehow explain why no possible route will get you to an empty stack, which is a little more difficult sometimes. All right. Can I say we are usually not going to write the stack derivation in this way, just because it's kind of a pain to write all of these steps. I will show you kind of our shorthand. It's not much of a shorthand. I mean, it's basically the same thing, but I'm just going to copy this down so I don't have to scroll it. The way that we will typically write this is, so we'll write all of this business with pairs. So each individual row up there, I'm going to represent by a pair. And in the pair, what you see is the first thing is the input string, which remains to be read, followed by the contents of the stack. And then our book, because our book author loves cute different little arrows, our book uses this arrow with the little tail on it. Every stack derivation uses an arrow that looks like that in our book. Anyway, the next step is going to say ABB, comma, SX. And if you want to label the steps, number 1, number 2, number 3, they do that in the book like that. So that was step 1. Doing step 1 again gets me BB, SXX. Next, we did step number 3, which gets you to BB, XX. Next, we did step number 2, which is just BX. And finally, step number 2 again, was epsilon, epsilon, and that's what everybody likes to see when you're doing a stack derivation. What you want is epsilon, epsilon at the end, and that means it's accepted. Epsilon, epsilon means, this first epsilon means I read all the letters from the input, and the second epsilon means the stack is empty. So epsilon, epsilon means accepted. All right, so each one of these sort of individual pairs here, this is what you see first is the portion of the input remaining to be read. And then this is just the stack, right? All right, each of these little pairs here, they are called, you might see this in the book on the homework. Each pair is called an instantaneous description. Because each of those pairs represents like a snapshot of what exactly is going on in this step in the stack machine. And the book calls them IDs. How do you know if something is accepted or not? You just write out the IDs. That's what they say. All right. So anyway, AABB is accepted. Can we try a different string? How about just ABAB? How about that? Let's try ABAB. All right, maybe I'll copy my my rules here. So these are the rules. And the rules actually we always are going to write in a little table like that. Hopefully you can still see them on your paper somewhere. I was going to make it, I can do this. Yeah, okay. So I am going to begin with ABAB, comma S, right? You always start with just S on the stack and whatever your string is. And then you do the steps. I guess I should do step 1 first because I'm reading it A and popping an S. So step 1 is applicable. And it becomes now, can anyone say, what does it say after doing step 1 on this? The pair, yeah? Yeah, what's the whole thing say? You just told me the stack, which is right.
BAB.
Yeah, great. BAB SX, right? You read the first A, so that goes away. And now what's left is BAB, comma, SX. Okay, what am I going to do next? Yeah?
Rule 3.
Rule number 3, yeah, is the only choice. You might be tempted to try to do rule number 2, but because it's a read B, but this is a pop X, which is not applicable here. So you must do rule 3 at this point. It says, that's an epsilon read, so the string stays the same, but the stack pop S push epsilon. So it's just going to say X now. All right, next, I think now we can do step 2 because I have a read B and a pop X. So I'm going to do step 2 now. It says AB, comma, epsilon. And what do we do next? The answer is actually we're stuck at this point. There is none of the 3 rules can apply at this point. Stuck. And that means basically this string is rejected. Now, technically speaking, rejected means that no possible sequence of steps can get you to epsilon, comma, epsilon. So there is a little bit of work to convince yourself. So I got stuck when I tried to do it this way. Is there some other way I could have done it that would have actually worked? The answer is no. I mean, there weren't very many choices here. I think the only other way I could have done this is by doing the epsilon read at the very beginning. In the very first step, you are allowed to do rule 3, but that would make you immediately stuck. It would say ABAB, comma, epsilon goes, or it would say this thing goes to ABAB, comma, epsilon, and then you'd be stuck. All right, so in this case, all routes get stuck here. Technically, I only checked one of them, but I think there's only one other thing that you could have possibly done here. So ABAB is rejected. All right. Anyone have a feel for this this machine at this point? Can anybody say like what kinds of strings will be accepted versus what kinds of strings will be rejected? If I were to describe in words how the machine works is, you read A. Every time you read A, it puts an X on the stack but leaves S on the top. So you can actually sort of like read A bunch of times. The only way to read B is to get rid of the S on the top by doing the third step. Anybody have a feel for this? What kinds of strings will be accepted here? Yeah?
Is this A to the N, B to the N?
I think it's A to the N, B to the N. If you think about how the rules work, I think it's true that you must read all the A's first before you read any of the B's. The idea is when you do these steps, the only ones which are going to work is if you do step 1 several times, and then you use step 3 to clear off the S, and then you can do step 2 several times to clear away the X's. And how many times do you have to clear away the X's? It has to be the same amount of times that you did the step 1 to begin with. All right, so this one here, this machine has language A to the N, B to the N. Yeah, it's true. All right. Maybe not a surprise that this would be the first example that I do, because that's like the simplest example of a language that's not regular, right? So this is a nice stack machine for a non-regular language. All right, I got one more example. Actually, I got 2 more examples. I don't know if we can handle 2 more examples, but we'll do one more example. This is another appearance of a classic example that we talked about last time. How about a stack machine for balanced brackets? One of my favorite non-regular languages. One of my favorite context-free languages, right? Balanced brackets, remember, I'm talking about this will accept strings like that. That is a legal string, or this is a string that's actually in the language of balanced brackets because the brackets are actually balanced. So this one should be accepted. And if you recall from last time, the balanced brackets thing is actually quite complicated, at least for an ordinary human being like me to think about. But it's something that is handled very easily by a context-free grammar, and also something that's handled very well by a stack machine. As I mentioned last time, as a human being, the way that I would read through this is something like I would match up those 2 first, and then those match, and those match, and those match, and those match. And so it really is acceptable. But this is not, how could you do that by only reading through the string 1 letter at a time from left to right? The letters here, of course, are just the brackets, the left bracket or the right bracket. It actually works very nicely in a stack. The way the idea here is every time you see a left-hand bracket, you just have to sort of remember, okay, I'm sort of like going down 1 level into the brackets. So after I see this one, I'm like 1 bracket deep. When I see this one, I am now 2 brackets deep. When I see this one, I just went up a level, so now I'm 1 bracket deep again. I see this one, that's 1 more bracket, 1 more bracket. I'm now sort of 3 deep, and so on. You just kind of, I can just sort of, every time I see a bracket, I either like add on a finger or take away a finger. This, of course, you can do with the stack, right? You just put stuff on the stack when you see a left bracket, and you take stuff off the stack when you see a right bracket. It's actually a very simple implementation if you're using a stack. This is not the way that I would do it if I was just looking at this by hand. But anyway, here is how I would write this stack machine then. So every stack machine always looks like read, pop, push, like so. And when I see the left bracket, remember I said when you see a left bracket, you want to push something new onto the stack. This strategy that I just said, actually, it's not necessary to keep track of like the S being on the bottom of the stack. In the previous one, we wanted to make it so that you had to read all the A's first and then all the B's, which is why the A's always referred to the starting stack symbol. In this case, we don't really care about the starting symbol at all. So I'm going to say, when I read the left bracket, I pop S and push X. I'm just going to use X as a generic thing to use on the stack. And when I see sorry, I'm just now realizing I can do this in a better way. I'm going to do it like that. We'll just use S for everything. Like the fact that S starts off being on the stack doesn't really matter. I don't need two separate stack variables. It just means when you see a left-hand bracket, you should put more stuff on the stack. When you see a right-hand bracket, you should take something away, which you would write like that. You pop S, but then don't put anything back on. And I think that's it. Every time I see a left bracket, I put a new guy on. Every time I see a right bracket, I take a guy off. Now, put a new guy on, technically, just because of the way you always write this. You write it as take this off and then put back two of them. But that's the effect is to put a new thing onto the stack. All right, can we just try? Let's read the string up there and make sure it actually works. So let's try left, left, right. All right, this is the beginning. Now I'm worried about.
I don't think it'll work if you use SS, because if you start with S, then there's always going to be one more.
Yeah, since we start with one S, we're going to end up with one S, even if it really is balanced. All right, I was being too smart. I'm going to have to go back to the way I wrote it originally on my paper. I should know better than to try and get smart during class time. I'm usually smarter outside of class than I am in class. Maybe you're the same way, I don't know. So sorry about that. I'm going to do it like this instead. The purpose is to avoid this kind of off by one thing. Unfortunately, it means I'm going to have 3 rules instead of 2 rules. Sorry to change it up on you. So, what's the difference here? When I read the very first thing, it's got to be a left bracket. Of course, if the first one here is a right-hand bracket, then you should just reject it immediately. The first thing I read is going to be a left-hand bracket, and that will immediately turn the S into the first X. We also need this one here because if we're reading a left bracket but not at the very beginning, there's going to be an X on the stack, and then we have to add another X to the stack. Maybe it's possible to do this with only two rules in some fancier way, but I'm not convinced of that. Anyway, can we read this? Let's see if we can make it happen. So let's give rules numbers. Now, once we get more used to things, I'm not always going to label the rules by numbers. If you know what you're doing, it's usually not necessary. You can tell what I'm saying here. Yeah?
Does the balanced brackets language accept like left, right, left, right?
Yes.
It does?
Yes.
Because here it
Although, yeah, this stack machine doesn't. Okay, so can I change my answer to say no? Yeah, this stack machine, you will run the stack all the way down in the middle in that case. If that's what you're thinking. Yeah, this is a good objection. So let's say that this is only going to accept things which are enclosed in one giant bracket, and then on the inside it can have blocks of brackets next to one another.
But for the regular balanced bracket, it will accept the left, right, left, right.
You mean the
Like left bracket, right bracket, left bracket, right bracket.
yeah.
It would accept that. This is just like an alteration on it.
I'm not sure the details of you mean like the grammar that I wrote last time?
Yeah.
So I would say like from an abstract point of view, if you were talking to like some computer scientists about, like this is an important language, they will say, oh yeah, I think it's like one of they're not exactly the same, but they're like close enough that it's a little ambiguous. The grammar that I wrote last time I think was something like this. I think that was the grammar. And that one does allow what you said, left, right, left, right. Yeah. So this, I suppose the example that I'm doing right here is almost the same as that, but not quite. Yeah. Thanks. I'm going to erase that. Okay. let's do this. So you just go one bracket at a time. I see the left bracket first. Pop S and replace it with X. So I'm writing all of these guys again, except for I skipped the first one. And it will now say X. All right? And then I'm reading a left bracket with an X on the stack. This will be rule 3. It will just say, reading the first left bracket there, X, X. All right? Now I see a right bracket, which will kill one of the X's by rule 2. This is getting shorter every time. All right? I eliminated one of the X's. Next, I see a left bracket, which should increase the number. So that was rule 2. Next, I see a left bracket, which will increase the number of X's. X, X. All right. I see another left bracket, which will give me another one. Sorry. I find it hard to write these and talk at the same time. All right, I hope I haven't messed it up yet. Now I see right bracket, which will kill one of the X's. That's rule 2. Right bracket, left, right, right. Just 2 X's now. Another right bracket will kill another X. So this is rule 2 again. A left bracket gives me one last new one. Like that, X, X. And now I'm going to do rule 2 twice and we'll be done. There we are. Epsilon, epsilon at the end. Accepted. All right. So this is a typical stack machine. You can get A to the N, B to the N. You can get this balanced brackets language. We're going to do one more specific example next time, and then we'll talk about what's the relationship between stack machines and context-free grammars. I said like the point of the stack machine is to be like a machine version of the context-free grammar. So that's where we're going next time. All right, we'll have homework over the weekend as usual. Have a good one.